Okay, so hello everyone. Welcome to my talk about connecting the front end and the back end with SignalR and messaging. My name is Marcin Hoppe, and thank you for being here. We're getting closer towards the end of the conference, so thank you for having that energy to participate. And before we go much further, I would like to run a very quick survey to sort of get to know you a little bit better and get an understanding where your interests are. So let's start with a quick survey. I will ask a few very simple questions. So if you happen to be in the yes category, just raise your hand. So are you all software developers? Okay, so we're in a good conference then. So how many of you .NET developers? Okay, good group. ASP.NET developers in particular? All right, so no hardcore WinForms WPF guys, at least not many of them. So how many of you have used the library called SignalR? Okay, more than half the room. That's good. How many of you have used message queues before? Okay. A messaging broker that's called RabbitMQ in particular. Okay, not many hands. A messaging framework called NServiceBus. Okay, few hands still, that's good. And a key value store that's called Redis. Okay, so is there anyone who raised their hand for every question? Good. No hands up in the air, so that means that all of you will learn something new today. So the premise of this talk and what we will try to do in this 15 minutes is we'll try to connect the front end of an application with a back end in a full duplex way. And what I mean by that is we will take an application and we will want to introduce the snappy push notifications into it. But the twist is that we'll try to scale this application out. So there are 3 ways to go about this problem and to connect the front of an application and then the back end of it. And the first one is a totally synchronous way. This is thing that we would call an RPC, or remote procedure call. So the browser makes a request to the server side. The server sort of blocks the client side, does its work, computes an answer for the front end and sends it back. And between sending the request and getting back the response, the client is totally blocked and the server is busy doing its work. One step further into better use of resources on the server side is what I would call an async on the server. So you're .NET guys, so I'm assuming that async await and the task parallel library and then that programming paradigm is known to you. So this is the thing I'm talking about here on the back end. From a client perspective, from the browser perspective, it's all the same, right? The browser makes a request and waits until the server completes its work. Where the difference is on the server side. So the server may use async operations, and the thread that services client request is not actually blocked, right? So we may use the resources on the server side in a more robust and efficient manner. And one step further is when the processing on the server side is completely async, and also this asynchronicity starts to be visible on the client side. So the client makes a request to the server, and the server responds immediately that it will acknowledge. It basically acknowledges to the client library that it will service the request, and then goes on to process it goes on to process it in a totally disconnected way. And when it finishes the work, it needs to send a push notification to the client that it finished, and if there are any results of the work or the computation, and then those results are also sent in that push notification. And this scenario actually gives us very interesting capabilities for scaling the work on the backend side, because previously in both the synchronous and asynchronous and the backend scenarios, what were basically bound by the capacity of the server. So all the work that happens there needs to happen on the server. So we have no easy way of scaling out the server. If we want to do this, we need to add more servers on the front end and use a load balancer. Here in the totally asynchronous scenario, what we can do is we can split off the work to some other backend servers, right? So we may send a message to a backend server from the front-end web server, have the work be completed there, and when the backend server responds back, the front-end web server will find the connection to the client and push the notification. So in order to make this a little bit more tangible, we'll make a sample application that's called Ping Pong, which I will show you in a second, and we will take it on a tour from a very simple one client, one server version into a robust solution that's scaled out both on the web front end side and on the back end side. So we will take it for a spin. Before I show you the application itself, let me show you how it looks on a sort of from a logical standpoint. We will have a single page application that sends a ping request. You will be able to just enter a piece of text, and that piece of text will be embedded in a request. That request will be sent to the server side. The server will package it in a RabbitMQ message and send it to the backend server for processing. What this backend server will do is that it will just take this message and package in a response message that is called the ponk message, and the ponk message will be sent back to the web front end, and that will be pushed back. So this is the last pattern that we just talked about, packaged into a running application. So from a logical perspective, that's how it looks, but in order to make it a living and breathing creature, we need some technologies. So on the front end side, we will use a library that I mentioned, the ASP.NET SignalR, which is basically Microsoft's wrapper over the WebSocket protocol that allows bi-directional communication between the browser and the server. For the messaging part, we will use the RabbitMQ broker. That's also why I asked about it. And in order to make it a scaling possible, we will run the thing in an Azure Cloud Services emulator, because it will allow me to scale it very easily, and also it provides a built-in load balancer so that I can have multiple front-end web servers. So let's see some code, and I will show you the code, and I will also show you the application. Okay, so I'll start with the application. I'll just run it. Oh, sorry. Okay, so you see that the Azure emulator has started, and what we have in here is an extremely simple application, and we can type a text, like for example, hello, and we expect that this text will be packaged in a message, sent to the web front end, then to the back end, and it should travel back unaltered and should be displayed here on the right hand side. Okay, so what just happened is we got the response back. We can type another message, and it will travel through our system, and it will get back to us pretty quickly. So if we go and take a look on the code side, we first can take a look at the front-end side of things. And this glorious web page that you have just seen is here. Okay, so the bulk of work happens here when the document is loaded. We set up a bunch of stuff. We get access to, in SignalR, the thing that allows communication between the server and the client is called a hub. And hubs are available both on the client and on the server. Right now we're seeing the client side. So this is how we obtain the hub, and later the ping pong hub object will allow us to communicate with the server. Here's a method that will be called back from the server side. So this client pong function is actually the bit of code that will be executed in response to the push notification that the server will push, which I will show you in just a second. But here's the interesting bit. When we click the button, we use the hub, and using its server connection, we call the ping method. And the argument to the ping method is just whatever was hidden in or typed into this ping text box, which is this text box here. Towards the end of the presentation, I will give you a link to a GitHub repo where this application lives. So if this JavaScript code offends you, I strongly encourage you to submit pull requests to make it even better JavaScript. Okay, so the interesting bit here is that we called something called ping that doesn't exist really on the client side. What the SignalR library is doing, it will package the ping message along with its parameters. It will serialize it. It will open up the connection, the WebSocket connection to the server, and send it there. And when the server receives that message, it will use something that's also called the ping pong hub, but it will use its server-side counterpart. And if you compare the two, these are really very, very similar things, right? So here in JavaScript, you call ping and pass it a parameter, and here you have a method that's also called ping that the SignalR framework will just automatically invoke for us. And what happens here is we use the thing called message session. This is an NServiceBus thing that allows us to send messages over RabbitMQ. So what I have configured, well, in the global ASAX file, there's the entire configuration of NServiceBus, and the most interesting aspects of it is that we use the RabbitMQ transport. In here, we give it a connection string to the broker, and also we set up what's called the routing information. So we basically say that we want to route the ping message to an endpoint called the backend. And this backend endpoint is located in another C# project, and the key part of it is something that's also implemented using NServiceBus, and this is a handler for the ping message. So this is something that will also be invoked automatically by a different framework, NServiceBus in this case, when the ping messages arrive at the at the backend server. And all we do, apart from a little bit of logging, is that we reply to this message. So in NServiceBus, we don't need to, if we're just responding to messages to the endpoint that sent them, we don't need to configure routing, because each of the messages will contain the information about the endpoint that sent them, and the framework will use that automatically. As far as deployment is concerned, both of those are packaged here in a cloud service, an Azure cloud service that's running on my local machine in an emulator. If you go and look up the properties of this cloud service, there's something that's called the instance count. So right now, both my backend and my frontend are just one instance each. Right, same goes for frontend. So on a sort of infrastructure as a service to platform as a service and to software as a service, on the spectrum, the Azure cloud services are somewhere near platform as a service. Essentially, what you get is a VM really with a fairly restricted access, and for web roles you also get an IIS server. So that would be that's the like a bare bones way from the front end to the backend. And if we go back to the ping handler here, what we do is that we take the ping message and create a response message, which is surprisingly called the pong message, and we set up a text. We just take the text that we received, package it into a response message, and send back to the front end. And the front end side of things also happens to use NServiceBus to handle those messages. So here we have the same thing that we have just seen before. It's this time a Pong handler, so it's something that handles Pong messages. And here, apart from again a little bit of logging, what we do is we're using SignalR to get hold of the hub. It's here we grab the ping pong hub again, and we use that hub to send the push notification to the client. So here, if you're looking at the code and are wondering why I'm sending it all to all clients, this is mainly because as of now I have no way of actually distinguishing one client from another. So if we have our little demo here, and I will open up a new browser window. You will notice that I get a response from the backend server, but the original window also gets that response, right? And this actually leads us to a little bit of a problem, right? Because no realistic application can be expected to support just one client at a time. And in order to resolve that problem, what we need is a way to correlate the client session and the backend side exchange of messages over RabbitMQ. In other words, what we need is an Ariadne's thread that will allow us to, when the whole user interaction starts on the front end, we need a way to track our way back from the backend processing through the front end web server back to the original browser session. And we do that by appending something called a correlation ID to each and every message bit sent from the browser to the server, but also from the front-end server to the back-end server and all the way back. right? So we need some identifier that will allow us to distinguish all the different all the different sessions here. So there are many ways through which those correlation IDs can be transmitted. They can be added directly into or explicitly into messages. They can be sent out of bound, or they can be appended into metadata, like for example message headers or HTTP headers. Now there are two possibilities for who owns the generation of the correlation ID. So my question to you is, how do you think who should generate the correlation ID? And the interesting thing, it's not one of those fluffy, fuzzy, it depends kind of questions. There is an answer. Either of the two, well, there's only one of the two is actually correct. So who thinks that the client should generate the correlation ID? Okay, so who thinks the server sites should generate the correlation ID? Okay, so interestingly enough, most of you said that the server sites should generate it, and unfortunately, this is the bad answer. And the bad it's a bad answer because if we get back in here, all would be fine if the acknowledgement that's sent here would be, we could assume that it will always reliably reach the web browser. This, unfortunately, in any computer network, we cannot make that assumption. Because what would happen if the correlation ID was generated on the web server? Since the whole interaction is initiated by the browser, the only way for the browser to know the correlation ID is with the acknowledgement message. And since we cannot reliably assume that it will ever get back to the client because the connection may be lost, or the user might have closed their browser, or however many TCP/IP problems might have just taken place. If that happens, the client is left in a state that's essentially unknown. It doesn't have a correlation identifier, and potentially the whole server-side interaction is happily taking place, right? So there's no way for a browser to actually hook up into this message exchange and the conversation that's happening in the back end. On the other hand, if we assume that the client generates the correlation ID, they can happily send it over with the ping message, and the server doesn't need to transmit it with the acknowledgement message. And in such a case, if the client doesn't receive the acknowledgement message, it can just retry sending the ping message. The worst that can happen is that the client has seen the correlation ID before and therefore can mark the message as a duplicate and send another one, another acknowledgement message, hoping that this one will get through and the client will never retry again. And the rest of the stuff will follow completely. Let's see how that works from a code perspective. So from a coding perspective, we need to have something that we can correlate on. For this particular demo, I have decided to use the username as a correlation identifier. A correlation identifier can be something that's ad hoc and specific to, it can be a random number, a GUID, if we don't want to keep it related to the user session. But it often happens that the correlation identifier is actually very handy for it to be connected to either user identity or the session with the web browser. So what we've done here is, let me just fire it first and show you. Okay, so is the demo effect going on? So basically what I have in here is a version 2 of my ping pong application that will ask me for my username and use that username as a correlation identifier. Okay, so my little cloud on my laptop is just starting up. Okay, and the first thing that I see is a prompt to introduce myself. I will pretend that my first name is Darth. Okay, and I'll send a message to an old friend that says, hello, we meet again. Okay, I do a send. I get the message back, which is great. And if I now go and open a second window and introduce myself as this old friend, previously, if I send a message here, both Obi-Wan and Darth would both get the message, and I will say, hello, Darth. It's been a while. Okay, and if we switch back here, you see that none of those messages were delivered to my other browser session. If I now continue, the circle is now complete. Then only Darth gets it. If we go into Obi-Wan's window, he doesn't get it. So the correlation between the username and the exchange of the messages on the backend side is not working properly. So how does it work from a code perspective? How do we use the SignalR and NServiceBus and all of those APIs to add a correlation ID? To it. So on the front-end side, not much has really changed. One thing that has changed is that after I have submitted my login form, the username is attached to the query string. The connection hub.qs is something that allows me, it's a SignalR API that basically allows me to set query string parameters. Why that is important, I will show you in just a few seconds when we go to the hub. And the rest here, as you can see, looks totally the same, right? So we just get hold of the ping pong hub, or at least the client-side incarnation of it. We use the server object and send the ping method. This part works completely the same as the previous sample. The only difference is that now in the query string we are passing the username. And if we go to the hub, there's one. You can see that the ping message only has one difference. It attaches the username to the message itself. So for the messaging part, I have decided to put the correlation identifier, which in this case is the username, directly into a message. And the key difference here is not in sending the message, but in actually handling the connection. So in the onConnected method, which is called whenever the client connects to the server, I get the username from the query string and do something called groups add. And I add the current connection ID to a group whose name is the username. Why that is important, I'll show you when we move the message on our way back to the browser. But the groups functionality of SignalR basically allows me to you can think of it as a chat room. So it allows me to group connections and later on send messages to all the connections, to all the browsers that I have in a group. In this solution, I have chosen to have always just one connection in a group, so that essentially I have a private communication channel with each and every browser. If we go back to the ping method, we again use NServiceBus to send the ping message, now with a correlation identifier, into our backend server. And our backend server is virtually untouched. The only other thing that we do is that in the response PONC message, we also embed the correlation identifier. So this ties back to when you saw in the diagram, each and every message is now embellished with a correlation identifier. And where this is crucial is in a PONC message handler in our frontend, because now we have the PONC message. The PONC message has the text, but also has a username. So we again get hold of the ping pong hub in here and use that hub to fetch all the connections in the group and send the PONC message back to the browser. So this is where the data goes, and this is where the correlation identifier ensures that we only send the message to the browser that it was intended for. Okay, so so far so good. The application looks much more realistic now. But the thing that we wanted to do is we wanted to scale it out. So what would happen if we add more instances of the front end, but also more instances of the backend side? Is there anything that could have gone wrong in such a scenario? So let's take a look. Let's imagine that we now have a web farm that has 3 front-end web servers behind the load balancer. So the SPA clients are connecting to some server, we don't know which one. We have the RabbitMQ broker, and we have 2 instances of our backend service. So our ping pong site is a huge success, and we're now scaling it out. So what we might see happening in here is that one of the SPA clients connects to, for example, web server number 1, because the load balancer has chosen that particular server. It sends a ping message to the broker, and now using the competing consumers pattern, one of those backend servers will pull the message off from the queue on the broker. So let's say that the backend server number 1 pulled the ping message, and it sent a response to another queue from which the web servers pull their messages. And it might happen that the response PONC message is processed by a totally different web server. And the problem is that this web server does not have a connection to our browser. So that's something that not only can happen at a sufficient scale, this will happen, and it will happen often, right? So if we want to scale out, the solution that we have, that we currently have, is no good. So in order to solve this, we need a component that's called a backplane. And a backplane in electronics is a common bus that connects all the different components on a circuit board in order to deliver power to them. So what we need here is a way to connect all the front-end web servers so that they can properly handle PONC messages, so that the one that actually has the connection to the client is able to process it. So the idea here is to actually, whenever there's a there's a communication we want to do with a client, we want to duplicate it across all the different web front-end servers. So how does it look with SignalR? SignalR has built-in support for the Backplane. It's a matter of installing just a single NuGet package and just configuring what kind of technology we want to use to implement this. Backplane. So out of the box, there are a couple of ways to do this. One way of using it, which I have chosen for this demo, is Redis. The other two that are out of the box available are SQL Server and also Azure Service Bus. So if you're using Azure, then that might be a better option. So let's quickly see how that works. So again, our SPA client sends a message to our web form. The load balancer selects web server number 1 again. Web server number 1 sends a message to the broker. Again, backend server number 1 picks the message, and yet again, the web server number 3 fetches the message from the broker. And the magic that happens now, because we're at the point that we have been here before, right? And the problem was that web server number 3 doesn't have the connection to the client. But what it can do is it can notify all the other web servers that, okay, there's something that should be sent to client number 1, the SPA application up there. So what it does, it pushes this information to the Backplane, and the Backplane is actually responsible for sending this information to all the web front ends that work with a particular Backplane instance. And now the web server that actually has the connection to a given client that started all of this can send the message to that browser. And if you're thinking, how is it possible? How does he know which one of those web servers actually has this particular connection? Is through a correlation identifier. Remember that each of those messages has a correlation identifier. So web server number 2 and number 3, they will receive the message. They say, okay, it's a connection ID ABC, and I don't have the connection ID. I don't know what client that is, so I'll just back off. But one of them, actually web server number 1, will take a look. Okay, it's a connection ID ABC. I have that connection, so let me send it to the client. And that's how the Backplane actually solves the problem, and the client is happy with having to get this message. Okay, so let's see how that works. Okay, so the third version of our demo is completely the same, except for the fact that it does tell SignalR to actually use Redis. And it has an additional NuGet package installed, and that's it. The rest of it is actually handled automatically by ASP.NET SignalR. If we go into, actually the interesting bit happens in the Pong handler. If you see it, the code that processes the response Pong message is actually completely the same. The reason that it can be completely the same is that this group thing, when it gets a correlation identifier that it doesn't know this group, it will just do nothing, right? So what this group thing does is it sends whatever is after the dot to all the clients in the group. And for web servers 2 and 3 that we saw, this group is empty, so there's no action. If we run this thing, Okay, so we run this thing, and just one thing that I want to show you is that here we have, you can see that I have 3 web front-end instances. Unfortunately, it's with the Azure emulator, it's not easy for me to show you how many backend instances I have. I can show you the configuration in a minute, but the rest of it works perfectly fine. Okay, so this message actually might have gone through any of the front-end instances. If I killed one of the front ends, my client will reestablish the connection to one of the other 2, and the whole thing will work again. Okay. So actually scaling out with ASP.NET SignalR is actually fairly trivial. The thing that makes it work is, at least for me, it was non-obvious, but the whole thing really depends on the collaboration between the client and the server. So the client, every SignalR client keeps like a cursor. It keeps track of how many messages it received from the server side, and if it connects to a SignalR hub on a server, it will send this cursor, and the server will send back all the messages or replay back all the messages that it has for this particular client that it hasn't yet consumed. So if the client reconnects, the duplication of the messages made by the backplane actually ensures that the client will still get all the messages it needs. So if you were to take away just 3 things from this presentation, is that you can scale out your backend with message queues and competing consumers. So this is the easiest way to actually, if you have an architecture that works in the truly async way, and your interaction of your front-end web server with your client is totally synchronous and based on push notifications, you can actually decouple your backend and scale it with message queues and competing consumers. One thing you have to do to make it work is you have to correlate your front-end user session with the backend message conversation. The message conversation that we've shown here is extremely simple, right? It was just a replay or request and response. But I imagine it could be much more complicated. It could involve more endpoints. It could involve pub/sub, whatever. If you attach a correlation identifier to the entire backend processing message exchange, you will be good. And the last thing is, if you're scaling out your front end, use a backplane to ensure that the proper client always gets the message, irrespective of which web front end handles the message from the back end. If you want to fiddle with the code, it's on GitHub. You can take a picture of it. The bit after the link shortener is fairly cryptic, but I ensured that the whole repo name would be even harder to remember. To play with it, you need RabbitMQ, obviously, and you'll also need Redis, and you will need the Azure SDK. Azure SDK, fairly easy to install from within Visual Studio, no problem here. RabbitMQ and Redis, my little cloud on my laptop was running them in a Docker container, which is also a fairly convenient option. So if you're curious about more of this, you can go into this link. It contains a recording of a webinar that we did, that the company I work for did on did some time ago on this very topic. So if you want to go slightly deeper than we did today, that's a good resource to have. So again, it's fairly easy to remember, I think. Okay, and last bit about me. Don't be strangers. I'll be hanging around in the hallways for some more time. I work for a company called Particular Software, and I have a disclaimer to make. We make one of the products used in the presentation, which is the NServiceBus framework, but any other messaging framework that we could use, like Mass Transit or Rebus, if we're staying in a .NET space, would work equally well. So if you want to shoot me an email, which I encourage you to do, feel free to do so. It's my private email address and also the company one. So get your pick. And also you can follow me on Twitter. And these days all my professional activities are on GitHub. So if you want to follow that, then that's great. Okay, so that's all for me. Thank you for being here. If you want to just shoot me a question, you can ask now or just join me here. I have some NServiceBus stickers, by the way, so if you want to grab one, you're free to go. Okay, thank you.